This is a standard electrode potential series. Depending on which syllabus you study, you may know this as the electrochemical series. You can see we have half cell equations as well as we have some voltage values on the right side of the table. Now this is sometimes known as the standard reduction potential. So let's find out why. Before we go on, if you enjoy educational content like this, please don't forget to hit the subscribe button. I produce at least one video a week. And if you're learning something, if you have learned something so far in the video, please do help me by hitting that like button. Now let's get on with the lesson. First, let's look at the general structure of this standard electrode potential series. If you look at all these half cell equations, these are half equations of substances accepting electrons. So all of them are of substances accepting electrons. When substances accept electrons, it means that they are being reduced. Reduction is the gain of electrons. So these are all reduction reactions, and that is why this is known as standard reduction potential. So this value that we see here, let's focus on the numbers on the right side of the table. You can see the pattern. It starts with the most negative number, and then as we go down the series, it becomes more and more positive. So it becomes 0 when we reach hydrogen. When we reach the half cell equation of hydrogen, it is 0. Then from hydrogen going down, it is all positive. And the value becomes bigger and bigger and bigger. So it keeps becoming more and more positive as we go down the table until we reach fluorine, which has the largest positive value here. So this is the general structure of the table. So how do we get these standard reduction potential values? How do we get these numbers here that we see on the right side of the table? Now, this is dependent on what we call the standard electrode half cell. First, we need to be clear that a potential difference can only be established when there are two half cells. So it cannot be based on a single half cell. Now the half cell that we choose as a reference for this purpose is hydrogen. So this has been assigned. That is why hydrogen is given the value of 0. It is very important that you understand throughout this video that the values are relative to hydrogen. I will cover the combination of different half cells in another video. In this video, we're going to focus on the standard electrode potential series and the standard hydrogen electrode half cell. Let's first take a look at what the standard hydrogen electrode half cell looks like. So this is what we have. We have hydrogen gas being fed in, and then we have a platinum wire that is connected to a platinum electrode. This platinum electrode is coated with platinum oxide. This is simply to increase the surface area of the ions that are in contact with the electrode. So then in the solution we actually have an acid containing 1.0 moles per dm cube of hydrogen ions. So when we call this a standard hydrogen potential, there are certain conditions that need to be fulfilled. First of all, the concentration of ions in solution, in this case, since this is a standard hydrogen electrode, we'll be looking at the hydrogen ions. The concentration of hydrogen ions must be 1.0 moles per dm cube. Second is the temperature. The temperature must be 25 degrees Celsius or 298 Kelvin. And then the pressure of the gas here, since the gas is involved, hydrogen gas is being fed in. I will get to that in a while. But the gas pressure must be 1 atmosphere or 101 kilopascals. Only when all these conditions are set, then it is called a standard hydrogen electrode. So what is happening to the hydrogen gas and the hydrogen ions? Again, when we look at our standard electrode potential series, it is written as a reduction reaction. So what is happening here is that the hydrogen ions, the H plus ions, are going to accept electrons right here. They're going to accept electrons to form hydrogen gas. So this is what is taking place at this electrode. Now again, we cannot measure the potential when it is not connected to anything else. So we have to connect it with another half cell. Now let's look at the negative portion first. Let's take zinc as an example. So we have zinc. You can see the value here is negative. Now, why is this negative? So let's say we have a zinc electrode, standard zinc electrode. This is what a standard zinc electrode looks like. It is very similar. We also have a solution containing 1.0 moles per dm cube. This time it has to be zinc ions because the metal involved is zinc. The electrode is zinc. Earlier the electrode was hydrogen, therefore there's hydrogen gas. We can't have hydrogen in solid form in standard conditions, so we use an inert electrode. That is why we use platinum. Platinum is not going to get involved with the reaction. But when we are dealing with a metal half cell, when we are dealing with a standard metal electrode, then we use the metal as the electrode, such as this case. We are looking at the zinc electrode and therefore we use zinc as the electrode, and the ions in solution will be zinc ions. So we need to supply 1.0 moles per dm cube zinc ions. This of course will come in the form of salts such as zinc sulfate. We cannot measure the electrode potential by simply using a half cell. You need to connect two half cells in order for us to get the value for the potential difference. So how do we do that? Again, our reference here is the hydrogen, the standard hydrogen electrode. So we are going to use the standard hydrogen electrode and pair it with all the other metals to find out the value that we see in the standard electrode potential series. So for example, this is how two standard electrodes are connected, two half cells are connected. So we can see on the right we have the standard hydrogen electrode, and on the left we have the standard zinc electrode. And these are connected, you can see the connection point. They are connected through wires and then they are connected to a voltmeter so that we can get the potential difference that is formed when these two cells are connected. Now notice in the middle we have something that we call the salt bridge. Now I'll get into more detail in that in another video when I talk about voltaic cells. All you need to understand now is that the salt bridge ensures a continuous flow of electrons because it prevents a buildup of charge. So let's look at what happens here. Between zinc and hydrogen, zinc is better at donating electrons. Zinc is a metal. Zinc is more electropositive than hydrogen. Now since zinc is better at donating electrons than hydrogen, what is going to happen is, in this circuit, zinc is going to be donating electrons out from the electrode here, and then the electrons are going to go in to the hydrogen electrode. So in this case, hydrogen electrode is the one that is accepting the electrons, whereas the zinc electrode is donating the electrons. Now this is very important because now we can establish our terminals. So you have to remember that current flows from positive to negative terminal, but electrons flow from negative to positive. So in this case, electrons are flowing out of zinc, which will make zinc the negative terminal. So this is our negative terminal and hydrogen is the positive terminal. So this will change depending on what hydrogen is paired with. In the case where the other electrode, the metal is better at donating electrons compared to hydrogen, then hydrogen will become the positive terminal and the metal will become the negative terminal, such as this situation here. Now since zinc is the negative terminal, the value that we get, 0.76 volts, is given a negative value. This is why zinc has a negative standard electrode potential. Now let's just go back to our standard electrode potential series. Let's look at zinc first. So we know that zinc did not accept electrons as is written in the standard electrode potential series. Instead, zinc donated the electrons. So we can apply this for all the other negative values as well. So if the standard electrode potential value is negative, it actually means that the reduction reaction did not take place. Instead, the oxidation reaction took place. Keep in mind, this is when it is paired with hydrogen. So actually what happened was zinc donated electrons to become Zn2 plus ions. So this is actually what took place. So let's apply this generally. When we have another standard electrode that is paired with hydrogen electrode, standard hydrogen electrode, and the value in the table is negative, that means in this case hydrogen is the one that has accepted the electrons and the other metal has donated the electrons. So for example, let's take tin, Sn2 plus. So we can see the value is negative 0.14. This means that when tin is paired with hydrogen electrode, what will happen is tin will be the one that is donating the electron. So it will act as the negative terminal and hydrogen will be accepting the electron. Then what do the different magnitudes mean? Now, as we go higher and higher up the table, further and further away from hydrogen, you will notice that the values become more and more negative. The magnitude becomes bigger. Now, this simply means that the higher the position of the metal above hydrogen in the series, the better it is at donating electrons. So the potential difference that is formed is larger. Now remember, the negative value here simply signifies that the metal that is connected with hydrogen is going to be the negative terminal. But if we look at the magnitude of the potential, you can see that it is increasing as we go higher and higher up the table. What this means is that as we go higher and higher up the table, whatever metal is at a higher position will be better at donating electrons. So when it donates electrons, what is going to happen is it is going to be oxidized. Oxidation is the loss of electrons. So the opposite is going to take place here. Now let me use metal M. Let's say we have metal M. When it loses electrons to form metal ion Mn plus and N electrons. So when it loses electrons here, what happens is M has been oxidized. M is oxidized. Now when the metal itself is oxidized, it is acting as a reducing agent. M acts as a reducing agent. So it is always the opposite case. If it is an agent of reduction, that means it has to supply the electrons for another substance to be reduced. That is what a reducing agent means. Now, in supplying electrons for another substance to be reduced, it itself is being oxidized. So, same will be for an oxidizing agent. An oxidizing agent is going to be reduced. It is an agent of oxidation. It is going to cause another substance to be oxidized. So, how is it going to do that? In terms of electron transfer, it is going to take away electrons from that substance. When it takes away electrons from another substance, that substance is going to be oxidized because oxidation is the loss of electrons. So by taking it away, it itself is going to be reduced because the oxidizing agent is going to gain electrons. So when we look at the standard electrode potential series and we look at this value, this is a highly negative value, which means this reaction is very unlikely. The opposite reaction is very likely. This will also mean this lithium ion is not a good oxidizing agent because it is not likely that it is going to be reduced in this way. The opposite reaction is more likely. Lithium is more likely to donate electrons to become lithium ions rather than lithium ions accepting electrons and being reduced to lithium. So it's a very, very weak reducing agent. But as we go down, the value becomes more and more positive. So it's heading towards 0. So these ions here are going to be more and more likely to accept electrons. Now, when we go below hydrogen, so now we've reached hydrogen. Now, when we go below hydrogen in the standard electrode potential series, you will notice that we have positive values. So let's look at copper as an example. So let's say now we pair the copper electrode with the hydrogen electrode. Let's look at the standard copper electrode in isolation first. Of course, for a copper electrode, the copper metal acts as the electrode, and this time the solution will contain 1.0 moles per dm cube copper 2 ions. So we have copper 2 ions and the copper metal. This is a standard copper electrode. Again, the conditions are it has to be at 25 degrees Celsius and the concentration must be 1.0 moles per dm cube. Now let's look at what happens when it's connected with the hydrogen electrode. This is the cell that is formed when we have copper electrode and hydrogen electrode. So the standard electrode potential difference that is formed here is 0.34 volts. Now in this case, hydrogen is better at donating electrons compared to copper. Hydrogen is more likely to donate electrons compared to copper. So the electron flow is going to be out of the hydrogen electrode and into the copper electrode. So in this case, the negative terminal is actually hydrogen. Hydrogen acts as the negative terminal, whereas copper will act as the positive terminal. So in this case, this magnitude of 0.34 volts, when the copper electrode is connected to the hydrogen electrode, so copper is assigned a positive value this time because it is the positive electrode. So when we look back at our standard electrode potential series, all the substances below hydrogen in the standard electrode potential series have a positive value, which means hydrogen is better at donating electrons compared to all these substances below it. Now again, we have to look at the magnitude. So if you look at the magnitude, again as we go down the standard electrode potential series, the value is becoming more and more positive. The reason for this is the same as what we saw earlier. As we go down the standard electrode potential series further and further away from hydrogen, hydrogen is going to become better and better at donating electrons compared to the other substances as we go further and further down. So this will create a larger potential difference when the cells are connected using the two electrodes. Now in the case where we have positive values of standard reduction potential or standard electrode potential, then these are actually going to be reduced because they are going to be accepting the electron from hydrogen. So when we have positive values and a cell is formed by combining these substances with positive values with the hydrogen electrode, this is very important. We are doing everything now with 1/2 cell being the standard hydrogen electrode. So when they are connected in that way, what is going to happen is these substances are actually going to be accepting the electrons. This means that these substances are very likely to be reduced because they are going to be accepting the electrons and they are acting as oxidizing agents in this case. Let's just take copper as an example again. So if copper 2 ion accepts 2 electrons to become copper, what has happened is copper 2 ions have been reduced. Now, by being reduced, copper 2 ions act as the oxidizing agent because it is accepting electrons from another substance. By taking electrons away from another substance, it is causing that substance to be oxidized. So this is where it acts as an oxidizing agent. So as we go further and further down the standard electrode potential series, what we will find is that the substances that are at a lower position in the standard electrode potential series are better oxidizing agents. Now it's important to remember that we are strictly referring to the ions and not the substances on the product side of the equation. For example, if we were looking at calcium, we are not talking about calcium metal. We are talking about calcium 2+ ion being a weak oxidizing agent. So when we look at all the elements here, fluorine will be the strongest oxidizing agent. It is at the lowest position, so it is the strongest oxidizing agent. Whereas when we go to the other end of the table, we can see it is occupied by lithium ion. So lithium ion is going to be the weakest oxidizing agent because it is at the topmost position. So again, we are not talking about the product side, we are not talking about lithium metal, we are talking about lithium ion. Now let's look at the product side of the half equations. So as I mentioned earlier, the metals at the top position, at the higher position, especially when we are comparing with the hydrogen electrode, the metals that have a negative value are more likely to donate electrons rather than to accept electrons. So in this case, when we look at the product side, these are the metals such as lithium. So lithium metal here is most likely to donate electron compared to all the other elements in the standard electrode potential series, which makes this lithium metal the strongest reducing agent, because it is the most likely to donate electrons and to cause other substances to be reduced. So this is the strongest reducing agent. So again, here we are talking about the metal itself and not the ion. The ion will be the weakest oxidizing agent, but the metal will be the strongest reducing agent. So you can see they are opposite, and this makes perfect sense. If the substance is more likely to donate electrons, then it is unlikely that it will accept electrons. It cannot be both. So let's go to the other end of the standard electrode potential series. So when we look at fluorine here, fluoride ion is very unlikely to accept electrons because fluorine is very likely to donate electrons. So fluoride ions here are the weakest reducing agent because they are not going to be oxidized. Instead, fluorine is very likely to be reduced to fluoride ions. So again, let's go through the general story. As we look at the standard electrode potential series, at the highest position, we have lithium. Now, lithium is most likely to donate electron. So when we look at this half equation here, this equation is unlikely to take place. What is more likely to take place is the opposite equation of lithium donating electron instead of accepting it. Now, as we go down the standard electrode potential series, you can see that the values become less and less negative or more and more positive. So as we go down, the metals or the substances are less likely to donate electrons. So for example, if we were to compare zinc and nickel, since zinc is at a higher position, zinc will have a more negative value compared to nickel, and zinc will be better at donating electrons compared to nickel. Then as we go down, we reach hydrogen, the value becomes 0 because this is the electrode that is chosen as the reference. Hydrogen is our reference to get all these values. All these values will only be obtained when one of the half cell is a standard hydrogen electrode. Otherwise, we would get differing values, and that is another video. So as we go down, it becomes more and more positive. Now as we go down to the furthermost, fluorine, then it has the most positive value. So it is the most likely to accept electrons compared to all the other substances in the standard electrode potential series. If you've stuck around to this point, thank you for watching. I'll see you in the next video.